Numerical models for the study of mechanical properties of long fiber reinforced composites. Measurement and analytical models of long fiber reinforced composite structures designed to study mechanical properties are generally able to provide only limited information. This is due to the fact that the measurements are limited by the possibilities of positioning of the sensors and also by the fact that some properties cannot be measured well, for example, the distribution of the main stress and deformation in the composite structure. The knowledge of the distribution of the main stresses and deformations in the structure is important for assessing how the structure is changed and under which stress. In this case, the corresponding model simulation using numeric methods represents a significant support for the development. Very suitable is to build model simulation in finite element method, FEM, but other numerical methods, such as discrete element, DEM, boundary element, BEM, or finite volume method, FEM, method, are also available. The mechanical loading of composite causes many different processes in the inner structure that varies with the actual deformation. Therefore, it is necessary to simplify or neglect some characteristic features in modeling of such structures. A major problem of mechanical properties modeling of composite structures is in particular the description of the principal stresses in short time delta t equals t plus 1 minus t. The solution of problem of composite with boundary conditions under tensile loading lies not only in the specification of the correct boundary conditions and material properties but also in the design of the proposed finite element mesh. The Fem programs are currently very sophisticated and allow the solution of a continuous problem transform into a final solution where the corresponding geometric simple subareas, finite elements, can be designed in the preprocessor. Let OMR 3 is the continuous area of the three-dimensional space in which the problem is solved. Its borders will be denoted gamma, where gamma is Lipschitz border, and let the approximation of the selected base functions is derived above each finite element of length element, because any continuous function can be represented by a linear combination of algebraic polynomials converging to a continuous solution, that is, limit 0, 1. Thus, the Fem method can be understood as a special type of variation method by using the mathematical description of the problem solution. The current commercial software and Fem programs, for example, ANSYS, Abacus, Hermes, LS-DYNA, MARC, PAM-Crash, allow to assemble and subsequently solve a series of problems with nonlinear materials not only with elastic but also plastic behavior corresponding to the properties of the long fiber reinforced composite. Model simulations in Fem were performed for different combinations of reinforcement arrangements of long fiber reinforced composites, which are important for comparison with experiments and analytical relationships. This gives the material properties for numerical simulation of the strength characteristics of whole frames. This lecture describes the creation of two numerical models and their comparison. Continuum model. Extended continuous model with structural unit. Continuum model. Extended continuous model with structural unit. The simulations were performed for a complete assessment of the mechanical properties sigma 11, sigma 22, epsilon 11, epsilon 22, gamma 12, gamma 23 and elastic constants E11, E22, G12, G23, nu12, nu23, whereas also information explaining the shape changes of the samples observed especially during tensile stress. Model simulations were performed in the following steps. Creating two model simulations of the long fiber reinforced composite. Creating the corresponding mesh of finite elements of the computational model in the preprocessor. Defining the corresponding initial and boundary conditions. Assembling a material model of the long fiber reinforced composite. The evaluation and comparison of model simulation results in postprocessor. Creating two model simulations of the long fiber reinforced composite. Creating the corresponding mesh of finite elements of the computational model in the preprocessor. Defining the corresponding initial and boundary conditions. Assembling a material model of the long fiber reinforced composite. The evaluation and comparison of model simulation results in postprocessor. The Fem model was created in the concept of coherent continuum consisting of a surface geometry corresponding to the test sample with length L equals 100 mm, width B equals 20 mm, and thickness H equals 1.7 mm. The finite element mesh of the numerical model was created from shell elements, 2D elements, with a constant element size of 2 mm. The boundary conditions affecting the magnitude of the displacements and stress can be defined in two ways, that is, the boundary conditions of the first and second types. The first way is to determine the displacement and stress distributions if force conditions are known, that is, volume forces, surface forces, and nodal loads. The other way is to determine the displacement and tension distribution if the geometric conditions are known, that is, the size of node displacement, the deformations, and so on. Both ways can be also combined. It is mixed boundary conditions, as shown by Lee. Boundary and initial conditions for the model were made by the boundary conditions of the second type. One side of the sample was fixed against the displacement and rotation of node y equals re equals 0 in all directions, layout, and the opposite side of the edge of the sample was fixed identically, only in x direction, the movement was allowed, whereas ux equals 1 mm that corresponds to the deformation epsilon x equals 1%. The strain rate was 2 mm. Min-1. The boundary conditions are shown in Figure 5. Continuum Fem model of the composite reinforced with long fibers with defined boundary and initial conditions. The second numerical Fem model, which was created in the concept of structure unit, is formed from three components: fiber matrix, the interfacial interface, where the microscopic dimensions of such a model are closer to the more real composite. Such a model can be created from a structural unit with a 1, 2, dot, in fibers, wherein the volume geometric configuration, for example, structural unit is a cube, cuboid, sphere, can affect the volumetric quantity of fibers in a matrix VF, VM, as shown by Necker. The change in volume ratio VF can be given on the example of the structural unit of the cuboid, which is shown in the section in Figure 6. The structural unit consists of 6 fibers represented by circles with the same spacing μ, which are bounded by a matrix, rectangle. By changing of the spacing can then be increased or decreased volume ratio of fibers VF. The finite element mesh of the numerical model was created from a combination of following elements: brick elements, 3D elements, with a designed element size of 0.0002 mm defined for fibers in matrix, Figure 7. The influence of fiber spacing in the structural unit on fiber volume ratio. Structural Fem model of a composite reinforced with long fibers. It will be assumed that E11 equals sigma 11 epsilon 11, E22 equals sigma 22 epsilon 22, G12 equals tau 12 gamma 12, G23 equals tau 23 gamma 23. The problem lies in joining of fibers with a matrix because the interconnections form an interface. The structural Fem model assembling presents a problem of the determination of appropriate boundary conditions, which is important in terms of accuracy and model verification. Incorrect design may result in concentrators and singularities of stress. The boundary conditions are created by the second type, geometric boundary conditions, as follows: the perimeter surfaces of the model perpendicular to the plane of the stretching direction have defined symmetry conditions on one side, symmetry in axis y and z, and on the opposite side, the boundary conditions are not prescribed. On surfaces in the plane of the stretch direction, that is, in the direction of the z-axis, the displacements and rotations were not allowed ui equals re equals 0 in all directions. On the opposite surface of the specimen, the condition was the same, only displacement in the stretching direction was allowed. The displacement was defined constantly to the maximum strain 1%, that is, ux equals k. Epsilon x equals 1%, k dot equals const, with strain rate 2 mm min-1. Boundary conditions are shown in Figure 8 and Table 2. The material properties applied in both Fem models, Continuum model and the second Continuum model with the structure unit, are based on the generally known values reported by fiber and matrix manufacturers. The fiber and epoxy matrix parameters are listed in Table 3. The results of both numerical simulations have exhibited approximately the same stress at the defined strain epsilon I equals 1% under tensile load and applied direction for a given fiber reinforcement, carbon or glass. The resulting dependence of force on the displacement of the samples obtained from the models showed an approximately linear course, both for carbon and glass fiber reinforced composite. Figure 9 shows the tensile test for volume ratio VF equals 0.3, where carbon fiber reinforced composite with the epoxy matrix exhibits approximately 2.2 times higher force response than the glass fiber reinforced composite with epoxy matrix. The boundary conditions of the structural Fem model of the composite structure reinforced with long fibers. Fem model boundary conditions for obtaining elastic constants.